we've got Ivan Alba, one of our favorite math people. And today he's taking us through making sense of math. This is thinking that he's going to share with you that works at any level all throughout the mathematics progression. But he's going to focus in on some examples that will really bring it all home. You may want to take a quick snapshot or a screenshot of this page. We are the core collaborative, and you are the network that makes us strong. So these are all the ways you can get in touch with us, share what you're doing, and reach out for examples and ideas. And we look forward to hearing from you. There's Ivan's smiling face, and you'll be hearing from him. He is someone who's done a little bit of everything. He's been in education for 25 years. He's taught everything from elementary to high school. He's an international consultant all over the world. This is still in the States, but when we were talking just last week, he was up in Alaska. Had to be flown into a place you can't get to by car. But what he really does is he takes math and gets beyond the answer, gets beyond the process, and gets deep into the why of the mathematics. And that's what he's going to do over this next hour with us tonight. And he has a couple of sayings that I'll let him share, but every time I've ever talked to him about math and every time I've seen him present, he starts off with a couple of ideas. And he's someone wonderful to have in your school. He not only can share these thoughts and questions and examples clearly in English, but he's truly bilingual and will come to schools and do all this work entirely in Spanish or a mix. And you can see he's starting to put up Ivan's 2 rules. You can see math makes sense is rule number 1, and then everyone will be good at math is rule number 2. So with that, I'll hand it over to Ivan and let him take it away.
Thank you very much, Isaac. It's a pleasure to be here to support all of you that are joining us online and those who will join us later on. As Isaac was saying, these are my 2 rules. This is what I believe in. I believe that math makes sense, and I hope that you do too. And today we're going to be making sense of math, specifically looking at one of our favorite subjects, or maybe least favorite subjects, and that's division. So I get a lot of people asking me about how do we make sense of division with whole numbers, as well as division with fractions. So we're kind of play around with a gamut of ideas here. First thing that we're going to be doing is we're going to make sure that everybody here is very clear about the 2 models of division. There are 2 models of division, and I'll share with those in just a bit, as well as that there are questions that go along with those models. The second thing is to really understand how the standard algorithm has really changed over the years, especially since the introduction of the Common Core, as well as the TEKS for Texas, and seeing that the algorithms themselves may be very different than the way that we were taught. And the third thing that we're going to focus on today is looking at the visual representations that can support the work that we're doing with division. Often we focus so much on the symbolic manipulation and playing around with symbols like numbers or numerals, and we forget about how important it is to see the visual models of pictures that go along with it. I really feel that everyone here is going to get something out of this. At the very least, you're not going to go through the same thing that I went through when I was a student. When I was a student, my teacher taught me for division with fractions, she said, it's not for you to question why, just invert and multiply. And I want us to keep that in mind because that's the way that I was taught. And so we're going to think about mathematics a little bit differently than that. Before we get started, we're going to focus a lot on division with whole numbers and the way that we were taught. So let's go on to the next slide as we remember. In division with whole numbers, how were we taught at school? I'm going to give you a few mnemonics that I've seen and I've heard before. Number 1, does McDonald's sell burgers? And everybody knows McDonald's sells burgers, but this is the way that many kids are taught. And as you can see, there's a D, an M, an S, and a B, and we'll look at that in just a moment because this is the one that I learned. Dirty monkeys smell bad. Just remember that, children. Dirty monkeys smell bad. If you remember that, you'll get it. The third one is, this one is a little bit harder to remember, but daddy, mother, sister, brother. I hear a lot of teachers saying this. And how do the students understand whether it's daddy, mother, sister, brother, or daddy, brother, mother, sister? It makes it very difficult sometimes to keep them straight. All of those are in service of that last bullet we see here, which is divide, multiply, subtract, bring down. And that's the algorithm that we were taught, and they told us just do it. It's almost as if they wanted us to say it's not for you to question why. Just divide, multiply, subtract, bring down. And if we can click on the next piece, you'll see exactly what we saw when we were children. And so you can see right there that the question is how many sixes go into 7, and then you put that 6 below it, you subtract, you put the 1, you bring down the 5, and so on and so forth. Generally, when I ask students, why is it that you bring down? Almost every single time they have told me, because that's the next step. Daddy, mother, sister, brother. Dirty monkey smell bad. Does McDonald's sell burgers? It's that V part, it's the bring down, but they have no idea why. So what we're going to investigate today is a little bit of a different idea with division. It's going to, some people are comfortable with this by now, and some people are saying, well, it's not really the way I do it, but we'll see why. I'm sharing here a slide that talks about why the standards have actually changed, why the algorithms are changing, because this comes directly from the Common Core state standards. It's also where other states have not adopted the Common Core. This language is still in here. So I'm going to read this and focus on the highlighted parts. Find whole number quotients and remainders with up to 4-digit dividends and 1-digit divisors using strategies based on place value, the properties of operations, and/or the relationship between multiplication and division. Illustrate and explain the calculations by using equations, rectangular arrays, and/or area models. I want us to keep that in mind today because that's really how the standards have pushed us to different algorithms. And the algorithm that I'm going to share with you hits each of those that you see here. The problem is that the algorithms that we were taught, dirty monkey smell bad, may not be connecting those. Let's keep going. So here's where the fun begins, when we actually look at the chart. When I was taught division, we were taught to do divide, multiply, subtract, bring down. But let's look at it and what this really means. Before we do anything, I'm going to start off by sharing with you the two models of division. I'm going to return to that later when we look at division with fractions. So I'm going to write up here division. And I'll put a simple division problem here. The problem is 8 divided by 2 equals 4. Now, this problem's not a difficult problem. In fact, I'm going to even put here the dividend, the divisor, and of course, our quotient. When students think about 8 divided by 2 equals 4, we don't want them just to think of it as another fact to remember. It's not just another fact, but we want them to actually think about the quantities we're working with. So I'm going to create a picture of this. Here's a picture. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 dots that I've drawn. The first idea that children say is that when you say 8 divided by 2, what you're really saying is that you have 8 dots and you're grouping them into 2 groups. So here I'm going to create these 2 groups. One group here and one group here. That is one of the 2 models of division, and I'll name them in just a bit. The second way that we think of division could be looking at not 2 groups, but groups of 2. And so in this situation, instead of circling this direction, I'm just going to do it like this so that you can see how these 2 models are actually opposites of each other. In the first model, we all know that the 8 is the dots, but the 2 is the number of groups. The question is, how big are those groups? And the answer, of course, is 4. One of those groups is 4, the other group is 4. In the second model, we still have 8 dots, but we're saying not 2 groups, but groups of 2. So the size is known, it's just the quantity is not. And so we say, how many groups of 2? Let's see, 1, 2, 3, and 4. And so our quotient is the same quotient, it's just the model is different. And so each of those models has a question that goes along with it. And I'm going to write that question right up here. So here's the question we have. For the red one, the one we did first, the question is, if, and I'm going to write here dividend, is divisor groups, or if we do fractions, we're going to say of a group. But if dividend is divisor groups, comma, how much is one whole group? How much is one whole group? So in this situation, I'm just going to write down here, if 8 is 2 groups, and that's what we said before. If 8 is 2 groups, how much is one whole group? Well, 8 is 2 groups. One of those groups is going to be 4. It's not a difficult idea, but we're going to need this idea for later. The second, this question here is actually, we call this the partitive division. And partitive division just means that we're using a partition model of calling this divisor the number of groups. So the second model sounds like this. Now, if you think about these green circles here, the question is this: how many, and I'm going to put here, divisor are in dividend? How many divisor are in dividend? So in this case, how many 2's, the divisor, how many 2's are in 8? So it doesn't make it, it makes it easier to think of a question that's going to help you think of how many 2's are there in 8? Well, in this case, we have 4 2's in 8. This kind of question is, this kind of model is called the quotative, or some people call it the measurement model. So we have to think about division as either one of these 2 models, either partitive or quotative. And what's important to understand is not the name of these models. It's not that we're teaching students, this is the what you call partitive and this one's quotative. It's that every single division problem that they're ever going to get is going to be one of these 2 models. So that students, when they read a question, they're not looking for keywords, they're looking for the structure of the problem. In every way, it's either going to be a partitive or it's going to be a quotative model that we're going to be using. So as students read their word problems, they'll have much more success when they understand it's one of those 2 models. So with this in mind, let's go to an example problem with whole number division. So this would pertain to 3rd grade, 4th grade, 5th grade, 6th grade. Understanding that those 2 models will help us to get to the answer to a problem. So I'm going to give you a problem. Here's our problem. We have 729 divided by 4. Oops. Now let's change this. Divided by 6. Just for fun, we're going to change this. So 729 divided by 6. When I do this problem, we're going to do it in 2 parts. We're going to do part of the math on one side and part of the math on the other side. Some of you know this algorithm as a partial quotient algorithm. And it can be written in many different ways, but this is one of them. Imagine that I had maybe a pile of cookies, and I had 729 cookies. And I want to pull out groups of 6. So we're going to use the quotative model for this. Meaning I'm going to pull out a 6, a 6, a 6 every time. So when I do that, I could pull out one group of 6 and subtract 6 from here, one group of 6 and subtract 6. It could get pretty tedious and very long. So what we want students to do is we want students to start thinking about, let me think a little more efficiently here. I'm going to take away a large group of those 6s. So imagine that pile of cookies, and imagine taking away a big chunk of those cookies. I'm going to take away maybe 100 groups of 6. I'm going to take away 100 6s of cookies, which would actually take away 600 cookies. Next question is, if I took those away, how many are going to be left on the pile? There should be 129 cookies left on the pile. If I go to take away another group, so here we go. Maybe some people would say, go ahead and take 20. You already know what it is. But some students are not good with 20. So let's take away a different number. Let's take away 10 groups of 6. So I'm going to take 10 groups of 6 from that pile. That would be taking away 60 from that pile. And what we have left in the pile, right on the table, is 69 left. At that point, we may take another group, just the same size. We already can see the 60 in there. So we take 10 more 6s out. So we take 60 out of the pile, another group of 60, and we're left with 9 left on the pile. At this point, I'm pretty sure students would say, well, there's one more group left, so there's one more 6 left. So I take away that 6, and I'm left with 3. Even in 4th grade, when they're learning the long division algorithm, we really want students to understand that the remainder is a function of the divisor, or of the 6. So we might even say you can take away 1/2 group of 6 more, so we can take away that 3, and we're left with 0 on that table. At the end, we can tabulate how much we've actually taken. 100 6s, 10 6s, 10 6s, 1 6 and half more 6. So we have 121 and 1/2. So our quotient is 121 and 1/2 groups of 6s, or our answer is 121 and a half. Think about this idea as students are actually pulling away piles of cookies. My teacher didn't teach me it that way. My teacher said, what we do is we put our 729 divided by 6, and we say, before we say how many 6s go into 7, because that's what most people say, the first thing that we teach students to do is to ignore the place value of this quantity. To just, instead of thinking about it as 729, to only think of it as a 7 in order to continue to do this problem. And it looks like this. How many 6s go into 7? Only 1. We know that this is not 1. But our students are using that and saying, well, if I take 1 here, 1 times 6 is 6. I'm going to subtract that. I'm going to get this 1 right here. And our students say, well, wait a minute. This is this much. And now we bring down to 2. And now it becomes 12. But we don't see 12 in our cookies. The problem is that the algorithm that we were learning as children almost separates us from the context of the problem. And when that happens, it makes it more difficult to connect the two at the end when they're thinking about the word problem they were working with. One of the biggest ideas that I was talking about earlier when we said, how does the algorithm change, is that the algorithms now expect for place value. And unfortunately, we've eliminated some of the place value right here. We've turned this into a 7, not 700. We've turned that into 6, not 600. We've turned that into a 2 that gets brought down when we know it's 20, all for the purpose of keeping to the same algorithm that my teacher taught me. I said there were other parts in that standard that were different. One of them said to be able to see it, well, let's just go over here. We can see the place value in this. The place value is always kept alive. As well as when we look at this problem, it says that we have 729, and that is made up of 600 plus 60 plus 60 plus 6 plus 3. This is what makes up 729, all of which are easier to divide by 6, our divisor, using, as we call this, the distributive property of division. We distribute the dividing by 6 throughout the whole, all of these pieces. Now, if it troubles you to hear the word distributive property of division, just say multiplies by 1/6 and you have the distributive property of multiplication. It evens, everything gets taken care of in that way. So now we have the distributive property of division included within our algorithm when we start thinking about it in this way. But we also have other pieces. Remember it said rectangular arrays and or area models. So where does that come in? Let's see it. We really have an array. And our array is a 6 by 100. Now I'm not going to build this to scale. Inside I have 600 plus 60. Oh, I'm sorry. Let me start this over again. We have our array of 6 by 100, which is 600, plus 10, which is 60, plus 10, which is another 60, plus 1, which is 6, plus 1/2, which is 3. What I really have is I have an array. Just like it said in the standards, we want students to be able to see their division within an array. And here's our array. It's a 6 by 121.5. Essentially, we have this problem, 6 in 729, and our quotient is 121 and 1/2. I want us to think about this a little bit differently than my teacher taught me. Imagine this were a rectangle. Here's where the relationship between multiplication and division comes right to your eyes. If I have a rectangle and I know the two factors, the two sides of the rectangle, we multiply to find out what the inside of the rectangle is, or the array. When I know the area of the rectangle and I know one of the sides of the array, I divide in order to find out my missing factor. And so in this way, we're also connecting multiplication and division, seeing this as a missing side problem for division, or a missing product for multiplication. We see the array or the area model as the standards are asking for. We see the place value within all components of the algorithm. We also see the properties of operation, which is the algebra properties, all of which are devoid with the algorithm my teacher taught me. And I'm not saying that this doesn't work. I'm saying it doesn't work for the students. If what we want students to understand is division with the standards in mind, well, then what we have to do is we have to focus on that. And so our algorithms have since changed to algorithms that are built more on number sense, more on place value, more on the connection with the pile of cookies that we were talking about earlier, than what my teacher had shown me to do. Well, I'll answer more questions later on, but let's continue. Isaac?
You got it. Yes, so if you have questions right now, you can share those to the chat, share them on Facebook Live. We've been tracking everything you're sharing and thinking, and like Ivan said, we'll come back for those. We've had some great comments, lots of people really talking about how powerful it is for this to make sense and how much we all wish that we had learned in a way that made sense. Now I'll let you take it back, and I'll let you know any questions we have when we have time.
Okay, thank you very much, Isaac. The second part, I know a lot of teachers have been asking, and I know that I might have some primary teachers in the room. All of this work really connects with the primary by thinking about the visual models. I know that primary teachers are wonderful about pulling out visual models, but we're going to see how important it is when they get into upper grades. So when they get into 5th grade and 6th grade and we're doing division with fractions, we really want them to understand it, and we want them to be able to understand it through the visual models that pertain to it. So division with fractions. Let's move forward. Would you change the slide, please?
Sorry, it's stuck. There we go.
So here was the quote that I gave you from the beginning. It says, "It's not for you to question why, just invert and multiply." That's the way that I was taught. Unfortunately, questioning why is a component of mathematics, and we've failed our students and we haven't asked them to learn to question. When they get to middle school, there's a second version of that, and teachers teach keep, change, flip. So if you think about it, keep the dividend, change the operation from division to multiplication, and then flip the divisor so it becomes its reciprocal. So it's multiplied by the reciprocal. And if you see that picture right there, this is maybe a common poster you might have seen in a middle school classroom. You see 1/3 divided by 1/6. It changes. The reciprocal becomes 6/1, and then division changes to multiplication. So now you have 1/3 times 6/1, and then you multiply those two, and you say 1 times 6 is 6, and 3 times 1 is 3, and then you divide. So 6 divided by 3 is 2, and we get our answer. Wonderful.
In trying to make it simple, it's become so hard to remember.
Well, it has, but more importantly, when I ask teachers, why do we invert and multiply? And what is the meaning for invert and multiply? And how does that, why is that our algorithm? I want to push us in a new direction. I want to push us because what we have learned, and this comes from the California frameworks, it says teaching the multiply by the reciprocal method for dividing fractions without having students develop an understanding of why it works may confuse students and interfere with their ability to apply division of fractions to solve word problems. We saw earlier how the algorithm that we learned, divide, multiply, subtract, bring down, could keep students from thinking about the cookies, keep students from thinking about the algebra, the distributed property, keep students from thinking about the array models or area models or even a picture, and keep students from thinking about the meaning behind the algorithm. And so we don't want to keep students from that, especially once we get into fractions, since fractions are so difficult for students to understand if they don't have a strong basis in their work. So let's go back to the chart paper. I'm bringing back our original chart paper where we talked about division as partitive and quotative. So I want us to remember the question that we have. For the partitive question, if the dividend, the first number, is divisor groups, how much is one whole group? I'm sure it made sense to you when you found it was 4. When we look at fractions, we're going to say, instead of groups, we're going to say of a group. So remember that, and we'll put it together in just a moment. And in this second one, we're not going to change it at all. It says how many of the divisor, or 2, are in the dividend, or 8. So let's have some fun with this one. I'll do a few examples. The first example I'm going to do might be something between 5th grade and 6th grade, mostly 6th grade because 5th grade only thinks of whole numbers, but I'm going to put a problem up here. And I'm going to put 3 1/2 divided by a 4th. So in this situation, let's go back to the question. Now, the first question, the partitive question, sounds like this. If, and I'll just write it completely, if 3 1/2 is 1/4 of a group, comma, how much is one whole group? So if 3.5 is a fourth of the group, how much is one whole group? So let's see it. I'm going to give it a context. And the context I'm going to give it here is thinking about, well, let's say I have a gas tank. So you have your Prius or some small car, and you create a gas tank. So here's our gas tank. And I'm going to fill it up. I'm starting to fill up. Now I said if 3.5 is 1/4 of the group, so we're going to think about gallons here. If 3.5 gallons is the fourth of the tank, because the group is going to be the whole tank. So in the situation, I'm going to break it up into 4 parts. Here is this little part right here is 1/4 of the whole tank. And inside of this part, I'm going to put 3 1/2 gallons of gasoline. So as I do this, I have the question, if 3.5 gallons is 1/4 of my tank, how much is my whole tank? Well, if this is 3.5 gallons and it's a fourth, I have another fourth right over here. And that's going to be 3.5 gallons. Of course, the next quarter, because they're all equal, will also be 3.5 gallons. And I have one more quarter, which will make 3 1/2 gallons. And now, as I start putting these together, we have these two together would make 7 gallons. These two together would make 7 gallons. Put them all together, and we're going to have 14 gallons. And so our answer to this problem, our quotient, is going to be 14. Because if 3.5 gallons is 1/4 of my tank, well then that's a fourth, that's a fourth, that's a fourth, that's a fourth, 3.5, 3.5, 3.5, 3.5, and it would work the same way. So we can also think about this maybe as a race. You can think of this maybe as a race. So there's a race. Here's our race. Now think of it if 3.5 miles is 1/4 of the race. So you could say this was 3 1/2 miles. So if that's 3.5 miles, that's 3.5 miles, that's 3.5 miles, that's 3.5 miles. The total race is going to be 14 miles long. Any way that you think of it, it's going to be the same question. If 3.5 is 1/4 of the whole thing, what is the whole? Of which we go to the second question. Now, remember that was the partitive question, and we have the quotative question. Many of you are already familiar and are probably already going forward with this. And here's the question. How many fourths, how many quarters are in 3 1/2? How many quarters are in 3.5? Now you can think of this as money, or you can think of this as pies. I'm going to create this as pies for now. So we have 1, 2, 3 1/2. So I have 3.5 pies. Question is, how many quarters are there in 3.5 pies? Or how many servings of a quarter pie are there? So let's see. We're going to cut this one into quarters, this one into quarters, this one into quarters, and this one to be cut into quarters. We're just going to do that. And then a student, what we want students to do is we want them to count them out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. We now have counted out all of our quarters. Now we have all of it done, and our quotient is the same quotient, the quotient of 14. Now remember, the quotient of 14 means different things in a different context. Remember, they're two opposite models. But this is how we get our answer using a quotative question, like how many quarters are in 3.5. Our teacher taught us an algorithm for this, and I'm going to share with you that algorithm again. We take 3.5 divided by 1/4. We invert the divisor, and then we multiply. So it would look like 3.5 times 4, or even 4 over 1 if you want to think of it that way. So, when your teacher taught you to think this way, did they explain it to you this way? Did you see why we have 3.5 times 4? Did they share that with you? Because mine did not. Let's look at it. Notice in here, do you see 3.5 times 4 there? And I have a feeling that everyone can see 1, 2, 3, 4, 3.5. So our algorithm, 3.5 times 4, is demonstrated here. If we use the race idea, do you see 3.5 times 4? My teacher never taught it to me that way. So in the partitive model, it is very apparent where it comes from. Now, in the second model, the quotative model, how many 1/4 are in 3.5? Do you see 3.5 times 4? So sometimes it gets a little bit difficult to see it, but let's look. How many 4s are there here? There's 4 of them. So it's one group of 4 in that one. How many quarters in this one? One group of 4 in that one. In this one, one group of 4 here. And in our last one, there's half a group of 4, or 2. In total, we have 1, 2, 3.5 groups of 4. That's where we get our same number. I want us to think about how our teachers taught us was their limitations and what they understood sometimes. Because somebody taught them as well. It's not for them to question why. Simply invert and multiply. And what I'm trying to share with you is that our efforts are to get students to understand the algorithms that we work with. Not only because it's important for them to understand, but because the standards are expecting that, and the higher level mathematics is expecting all of this to happen. We expect students to make sense of mathematics. Just like I said in my 2 rules, math makes sense. So when we teach them to divide by fractions, we also want them to learn why it works. I often get the question though, is like, what if it doesn't come out easily? What do we do then? So I'll give you another example. Let's just write it. Let's just do one more example here. So I was thinking about a problem, and here's a problem. Let's do 5 divided by, well, 2/3. I know this is not going to come out well, but let's see both of the problems. Let's start off with the quotative model. The one, well, actually start off with the partitive, just like we've been doing before. So here it comes. If 5 is 2/3 of the whole of the group, how much is one whole group? Let's go back to our gas tank idea. Here it goes. Here's our gas tank. Let's put 2/3. So this amount here is going to be 2/3. And so how much is 2/3? Well, 5 is 2/3 of the whole thing. So this must be 5 altogether. Well, if these 2 pieces are 5, what's one of those pieces? Well, it's going to have to be half of 5. So I'll write that in here. Let me write that in green. In here must be half of 5, or 2.5. In here it must be half of 5, or 2.5. So if 2/3 is 5, what's going to be in this one right up here? Well, it should be 2.5. And so altogether, 3 2.5s or 3 2.5 must be 7 1/2. Again, using a model, we could figure this out. It doesn't, I'm not saying we don't do invert and multiply. I shared with you earlier that we can. But I'm saying that to make sense of it, our visual models are going to help us. Our second question, of course, is the quotative question, and it sounds like this. How many 2/3 are in 5? Let's find out. Here are 1, 2, 3, 4, 5 circles. Let's break them into 2/3 by breaking them into thirds. Let's count them out. 1, we want to find out how many 2/3 are there. There's one of them. That's another 2/3. That's another 2/3. Another one. Another one. Another one. Another 2/3. At this point, we have 7 2/3 and this amount left. Now, some of you might be thinking it's 7 1/3, but that's not how much this is. Because if I had one more slice of that, I would have put 8, 8. But I don't have that slice. I have half of what it takes to make 8. So my answer again is 1, 2, 3, 4, 5, 6, 7 1/2. So my quotient is still 7 1/2. And so even when the quotient doesn't come out evenly, we still have to interpret the remainder in terms of the divisor. And if the divisor is 2/3, 1/3 is half of a 2/3. 1/3 is half of a 2/3. And that's where we get our answer of 7 1/2. So let's go back to the slides, Isaac.
We got it.
So let's look at what we've learned. The most important thing that I want you to take away today is those two different questions. They're going to be the backbone of everything that we do. Go ahead and switch the slide. Those two models of division, here we go. The first one, the quotative model, I'm sorry, I flipped the two, but it says you know the size of the group. You're looking to find out how many of that group can be found. And it's characterized by the question, how many of the divisor are in the dividend? Let's move on to the next one. In part of the division, you know how many groups. You're looking to find the size of one of those groups. So it's characterized by the question, if dividend is divisor groups or in fractions of a group, how much is one whole group? So again, I'm going to give you the example. If 3 1/2 is 1/4 of a group or 1/4 of the gas tank, how much is the whole gas tank? And how many 1/4s are there in 3 1/2? Those are the two questions with the division of fractions involved. So our learning intentions today, identify the two models of division and the questions that pertain to each of the models. You just saw those there. To understand why our algorithms for division are actually different than the way that we were taught, specifically looking at the long division algorithm for whole numbers and why that's so important. And finally, being able to see a picture of those representations so they make sense to students the first time they hear about them and every time after that. Even if we're going to teach them an algorithm that works with symbols, they must understand how the pictures work with them.
Excellent. And we did have a question. What do you do when you're dividing these really large numbers? How do you use the visual representation for that?
When you say large numbers, I'm making an assumption that we're talking about large whole numbers, or
I think it was for whole numbers, yes.
Okay. So when we're working with whole numbers, it doesn't matter whether we're looking at very, very large numbers or even small numbers like decimal numbers. We're still finding the partial quotients. Instead of having, if you remember in our earlier problem, would you throw back the chart? It's almost easier to do it by looking at our.
Of course. Mm-hmm.
So when we looked at this, our numbers were 100 sixes. We could have 10,000 sixes, or we could have this number be a very different number, like 436. And how many of those are there in 13,478? We still need to think about numbers as in base tense, in our base tense way. So we think of them in hundreds or thousands of them or 10,000s of them. And you can still do the same work. But the idea is that students are thinking about the number sense within the quantities they're working with. So a very common thing that students might do is on the side of their paper, they might write 1 times 6 equals 6, 10 times 6 equals 60, 100 times 6 equals 600, and if they need, 1/10 times 6 equals 6/10, 100th times 6 equals 600th, and just writing down a list like this to help themselves to orient as they start to put these pieces together. I hope this helps, because this is really an important first step for many students to really understand the base 10 system and powers of 10 times that divisor. And when they do that, they're able to really make sense of all of what they're multiplying later on.
Yeah, thank you so much. And if we get more questions or thoughts, we'll reach out to you and share those. But I think we hit all the questions you had. And I know some of your questions were answered throughout the presentation.
Well, thank you very much. I know I try to be as thorough as I can when I'm working with teachers. Let's remember that math makes sense, and everyone will be good at math if we make sure it makes sense.
Excellent. So thank you so much to Ivan. We want to share a few things with you. We want to welcome the amazing Brian Roy. He's our Executive Director of Learning Partnerships, and he is someone you can reach out to if you want to have Ivan out at your school, or any of these other amazing people we have leading our Empowered Learner series. You can find out more about that at thecorecollaborative.com. We are coming back third Thursday next month. We're going to have Connie Hamilton really digging into the art of questioning, based strongly on her book, Hacking Questions. If you have not picked that up, do. It's an easy read, but there's a lot there. It's a book you can really sink your teeth into, but with great application, and she will be sharing some great things with us right before the winter holidays begin. We are so excited about this book coming out, Belonging Through a Culture of Dignity. Just last month, we had a great session with them. You can check that out on our YouTube page. And then you can look to thecorecollaborative.com and find out more. But this is a book and in a body of work that's really changing lives in and out of school. We're so excited about peer power and the impact this book is having. 13 outstanding educators came together to lend their expertise to this movement of shifting learning to the students. And so much of what Ivan's just shared with us really resonates with that, making it about the learning, about making sense, and about how this work can be applied by students. We're excited just right around the corner to be at the Learning Forward Conference. You can see we have some of our outstanding people are going to be there presenting, so we hope you'll come say hello, check them out, and learn with them. You can see there, you can get a quick screenshot or take a picture, and then find more information for that online. As always, reach out if you have any thoughts or questions. We were just talking about all these amazing things we're going to be doing at Mindfueled this year. Same great experience, but a brand new location in beautiful Vail, Colorado, and really working on some ways to help you enjoy this amazing place. You've still got an opportunity to jump in just in time for your holiday shopping. To register early and save some money. You can find out more at mindfuel.com. We really do hope you'll come join us. a different experience from anything else I've ever been a part of. And of course, as I said at the top, we are the Core Collaborative. So find out more, join our Facebook group. We want to hear what you're thinking, share your successes, and reach out with thoughts and questions you may have. And then we have excellent models of success on our YouTube page from all of you out there, from teachers and students alike. And you can follow us on those others. But I would just like to thank one more time for sharing his expertise with us and being willing to take time out of his day. Ivan, is there any last thought or wisdom you want to share with our learning network?
Sure thing. So let me come back to, there really is a lot of complexity within mathematics. Just because we went over this a little bit, I hope that you can then practice some of these on your own. Watch the videos again and see if you can try it out yourself. One thing is just to watch me do it, and the other one is to practice yourselves. Sometimes it takes us a few times to practice it so that we can do a good job with our students. And so there are manipulatives you can be using in order to support students. I know we don't have that opportunity here in the webinar, but that's part of what we do when we support the teachers, is understand how to actually do the teaching of this. Today was just a little glimpse, and there is quite a lot to understand about division as well as with the different algorithms that we work with. I want to remind everyone that math does make sense, and we can all make sense together. I want you to help me to help other people make sense of math and keep my vision alive. And my vision is that everyone will be good at math. So thank you very much for the time that you've dedicated to this, and I appreciate it all.
Yes, I just want to echo that. We're thankful for you and for all of our learning network, and we hope that everyone has a safe and joyful holiday. We will see you back in 1 month for our next session. And as always, thanks for sharing your two most valuable assets, your time and attention. And we will see you next time.